last lecture we have been discussing about the photoisomerization of benzene, and we just we looked at we mentioned that the benzene under photolytic condition gives three valence isomers. First one is dibenzene, other one is valence benzoylene and prismane. It has been found that the prismane is not the primary product, but is derived from the 2 plus 2 cycloaddition of dibenzene. We also looked into the mechanism for the formation of these photoisomers from benzene. The steps involved is the first benzene under photolytic condition goes to excited state. These excited states, we also mentioned that these valence isomers were formed by the reorganization of sigma and pi bonds of the benzene. So since under photolytic condition, we can excite one of the double bond, and then this diradical, and then it can form this radical. This isomer, and then it can undergo 2 plus 2 addition under photolytic condition to give prismane. So these all we discussed last time. Is just a review of last lecture. The formation of benzoylene is very important also in today's lecture, because next we are talking about the photoisomerization of substituted benzene, where it is assumed that the product is derived from benzoylene. Similarly, the excitation of benzene, excited state, 1,2 diradical, and then the formation of cyclopropane, and then this can recombine to give this product. Now, today we would like to see the photochemistry of substituted benzene, and it has been observed that 1, 2, 3, 4, 5, 6, 1, 3, 5 trideutereobenzene under photolytic condition undergoes photoisomerization to give you 1, 2, 3, 4, 5, 6. 1, 2, 5 trideutereobenzene. So this is the now here we can really see the photoisomerization, because in unsubstituted it is just we can't appreciate the photochemistry, but here we really appreciate the photochemistry of benzene, when we are talking about the substituted benzene. So, and it is assumed that the reaction occurs via benzoylene as the intermediate. So, as mentioned before, benzoylene is a very important intermediate for the photoisomerization of benzene, unsubstituted as well as substituted. So, this is an example where trideuterum benzene at different position, the photoreduction gives rise to trideuterum benzene with the shift to give to 135, going to give 125. Now let's see the steps involved. The steps involved in the photo transformation from this photoisomerization of 135 trideuterum benzene to 125 trideuterum benzene. As mentioned, the most important intermediate is the benzoylene. So which is formed by the excitation of one of the double bond, by the excitation of one of the double bonds. Say for example, say this one. And then this will attack here to generate a 3-member ring, and then this will go as a radical, and then this radical will attack on this carbon as a shifting of the double bond. This is the steps involved. If you really write stepwise, we can just we can see that the excitation of this double bond, these are the substituent, and then attack of this to give a new diradical species with a new bond formation. This one, these are the substituent. This will attack on this This will attack on this, and then this will shift to give. So this is going to give a product like this. And this was so we have just mentioned the dotted lines. This one of this, and then one of this. And in other cases, so this will be this like this. Just to say that if we cleave this, so there is a possibility of formation of benzene, and then the dotted line shows that the cleavage of the transformation of benzene for the to the product. So if we cleave this, we get a diradical. If we cleave this, we get a diradical like this. So we are just cleaving this one to give a diradical. So this is dotted line. We have cleaved this dotted line, so we have a diradical. This one, if we can number this 1, 2, 3, 4, 5, 6, substituent at 1, 3, and 5. Substituent at 1, 3, and 5. Now going to 1, 2, and 5. So how it is going? That's what we would like to see. So as we have mentioned, is going via benzene under photolytic condition, going via this as a main intermediate, and then cleavage of one of these the bond of benzene to give a diradical. So we'll just represent this. These are the substituent. 1, of course, we'll just 2, 3, 4, 5, and 6. We are not. So this is the diradical after the cleavage of this. So if we this will, and then we cleave these two, this one also. So we are just cleaving these dotted. So I'll just rewrite again and show that what we would like to see here. We would like to see, first one is excitation of this 1,2 diradical going to a benzene intermediate, and then this benzene intermediate undergo cleavage of these dotted lines. So we'll just cleave both and generate a diradical here and diradical here. Then we get this one, 1, 2, 3. This is a right diradical, this diradical. By cleaving of the dotted lines, these are the substitution. Deuterium. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? Now this radical and this radical form a double bond between this, and this radical and this radical will form. I will just write it stepwise. First, this radical form a double bond, so we get is already there. This is, so we are just forming a double bond here, right? And still we have this diradical is still remain. This is deuterium, D, and D, right? So and then this numbering 1, 2, 3, 4, 5, 6. Now this radical and this radical will form a double bond like this. So we get a deuterium. So we have a double bond here, and this is the new double bond which is formed by coupling of these two diradical. We have a deuterium substituent at 1, 3, and 5. Deuterium 1, 2, 3, 4, 5, and 6. But if you number this, because then this is what this benzvaline is transformed to this, and this is nothing but this is the same as this one. Now, if we can write this, we have a carbon number 1 is a deuterium here, and carbon number 1 is connected to carbon number 2, and there is a deuterium, and then 2 is connected to 3. Carbon number 1 going to 2, then going to 3. Carbon number 1 going to 2 and then to 3. There is a deuterium at 2 and then 3 and then going to 4 and then to 5 and 6. So, this is how you can see that the phototransformation of substituted dideuterium 135 is going to 125 photoisomerization. Whereas if we cleave these dotted lines, this line or this line, then we end up with the regeneration of a starting material. So, so this is how we can explain the rearrangement photoisomerization of substituted benzene, where 1,3,5 trideuterium benzene under photolytic condition goes first to the valence isomerization with the main intermediate, and then valence isomerization undergo the bond cleavage followed by bond cleavage and bond formation to give a this photo rearrangement. Now, and of course, the degeneration of this can also be obtained. So, if you go back, if the new bond which is formed, this is the new bond. This is the new bond which is formed. This is the new bond which is formed. This is, and if we cleave this new bond, you go back to your starting material. So, but new bond which is formed, if we explain the formation of the product, can only be explained by forming not the new bond form, but by the old form like this one and this one in the benzvaline as intermediate. And hence, the observation, the formation, it is experimental fact that when we irradiate 1,3,5 trideuterium benzene, it gives 1,2,5 trideuterium benzene, the experimental observation. And then, in order to explain this, you can say that this trisubstituted benzene going to a benzvaline as intermediate, which can undergo further reorganization, cleavage, and formation of new singular and double bond gives reformation of this reagent product. There is another example of the photoisomerization of orthoxylene. Orthoxylene under photolytic condition gives metaxylene. So, you can have a 1, 2, 3, 4, 5, 6 disubstituted at 1, 2 position. Now, after rearrangement, 1, 2, you can say that it's better to start from the substituent 1, 2, 3, 4, 5, 6. So, we have a substituent at 1, 3 position. 1, 2 position substituent and this 1, 3 position is substituent. So, it is a photo rearrangement of substituted dimethyl benzene to from 1, 2 to 1, 3, and let us see. And it is the reaction takes place via as usual, reaction takes place via benzvaline as a logical intermediate in this case also. As we have already seen, the main intermediate involved in the photoisomerization of trideuterium benzene to a 135 to 125 via benzvaline intermediate. Here also the formation of orthoxylene, metaxylene from orthoxylene can also be explained from this benzvaline intermediate. As usual, the benzvaline, we can the steps involved in the rearrangement can be visualized by looking into this mechanism, and you can say that as mentioned, the main intermediate is the benzvaline. Is the benzvaline as the main intermediate. Benzvaline as main intermediate in the photo rearrangement or photoisomerization for shifting of the 1-methyl group. So, 1,2-dimethyl goes to an excited state, and then this will get this gets isomerized to benzvaline that we have already seen in earlier cases in several examples. So benzvaline, and this, if we cleave this, as usual, if we cleave this, these are the bonds, these are the new bond formation, this is the new bond, this is the new bond, and if we cleave the new bond, you go back to your starting material, there is no reaction. But if we cleave the old bond, this is the old bond, this one, as well as this one. If we cleave this, then we end up with the product. So this will bond formation, you get a double bond here, a new double bond, and then this double bond. So if you can number this, because you have from 1, is the bonding goes to 3, 1, 3, and then goes to 2, goes to 2, 1, 3, and then 2, and then 4, and then 5 and 6. And you see the 3, there is no substitution, so you have a 1, 3 position. So 1, 2, 1, 2 going to 1, 3, photoisomerization of substituted dimethylbenzene can be explained via, once again, via this benzvaline intermediate. So in most of the cases, the photo rearrangement is the benzvaline is the main intermediate, and if we reorganize, cleave, and once again form the old bond, a new bond formation leads to back to starting material, new bond formation leads to the product. Hence, we can say that the just to summarize, benzene under photolytic condition gives 3 valence isomeric products: dibarbenzene, benzvaline, prismane. Dibarbenzene and benzvaline are the main primary photoisomers, whereas prismane is derived from the 2+2 photoisomerization of dibarbenzene. The formation of dibarbenzene can be visualized by this step. First, excitation of the one of the double bonds generates 1, 2 diradical, and then attack of one of the radicals at 4th position, 1, 2, 3, and 4th position to give this dibenzene, which will under photolytic condition undergo further 2+2 reaction to give this prismane. Another main important intermediate, benzvaline, can be once again formed via excitation of one of double bond, the formation of cyclopropane ring, and then further formation of another double bond between 1, 3 double bond, 1, 3 bond, and then 1, 3 bond can give this intermediate. And if you can write better way, it looks like this. Benzene, and in the case of substituted benzene, the trideuterium or dimethyl, in both the cases, benzvaline as the main intermediate, which reorganizes to give the rearranged product, that is the photo 1, 3, 1, 2 going to 1, 3, and then trideuterium 1, 3, 5 going to 1, 2, 5. Now, the next class of reaction in the case of aromatic compound is the photoaddition of benzene. Benzene undergo 3 different types of reaction: 1, 2 addition reaction, 1, 2 addition, 1, 3 addition, and 1, 4 addition. 1, 2, 1, 3, and 1, 4. So we'll just we will look one by one. First, we just see the 1, 2 addition, and it is found that the benzene under photolytic condition goes to an excited state, and then the excited state of benzene can react with electron deficient alkene. So this is one of the criteria, because benzene is electron rich, is a 6 pi electron, sextet is circulating all the way in all 6 carbon. So it is electron rich, and it can add to electron deficient alkene. Say for example, can add to dicyano. That's why it is X. This is a X and Y. They are electron deficient, being electron withdrawing group, and then that's why we can, if we can have electron withdrawing group as dicyano. So it has been found that benzene undergo electron deficient alkenes such as dicyanobenzene, cis or trans, to give the 1, 2 addition product like this. First, and it has been also assumed that the reaction proceeds via an exciplex formation. Exiplex, for instance, is a pi complex. The electron deficient alkene forms a pi complex with the benzene ring. Is formed a complex exiplex, and then this will add to 1,2 position, giving rise to a addition 1,2 addition product. So benzene undergo 1,2 addition product with electron deficient alkene, because benzene electron rich species can add to the alkene which has an electron withdrawing group, and in a 1,2 addition manner to give rise to a 4-membered ring. 4 and 6-membered ring is formed in the case of in the benzene. Some of the few examples are shown here. Benzene can lead to cis dicyanoethylene under photolytic condition to give this 1,2 addition product. 1,2 addition product. Examples of 1,2 addition. 1,2 addition product, and you can see that the stereochemistry is retained in the cis. Cis remains as cis, and where is a ring junction is also a cis ring junction. If you start with a trans alkene, electron deficient trans alkene photolytic condition also gives 4 and 6 undergo 1,2 addition. 1,2 addition and giving rise to, so here you can say that the trans, so cis gives cis, trans gives trans, but the ring junction remains the same, the cis ring junction, and that is true in the other side of this. Addition of benzene, so addition of benzene with the electron, the triple bond has also been reported. This is also 1,2 addition. Example of 1,2 addition is a dimethyl dicarbonate. Is a very very commonly used the dinophile dimethyl dicarboxylate, and then when the benzene under photolytic condition reacts with dimethyl dicarboxylate, also forms 1:2 addition product, 1,2 addition reaction to give rise to a product like this. CO2CH3. But since there is these two dimethyl dicarboxylate is a bulkier group, and there is a double bond here, is a 4-membered, is 6-membered, is unstable. And then it opens up to form a 8-membered So this is this acetylene electron deficient. This is electron acetylene. Electron deficient acetylenes have also been reported to add in a 1:2 addition manner with benzene under photolytic condition to give 1:2 addition product. 1:2 addition product with this dimethyl acetylene carboxylate is electron deficient because two electron withdrawing groups are present, and that's why it can also add in a similar manner as we have seen in the case of dicyanoalkene. So it also proceeds via the formation of exiplex, and then in a 1:2 manner to give, since dimethyl acetylene dicarboxylate is a bulkier group, and we have and it is connected to a bicyclic, the 4-membered ring, and then connected to a 6-membered ring, is highly strained system, and hence therefore this is unstable, and hence it opens up to give a cyclooctatetraene derivative. So this type of reaction has also been reported, where it has been shown that benzene under photolytic condition also undergo 1,2 addition with acetylene derivative, in addition to 1,2 addition product with electron deficient alkene derivative. As such as most important electron deficient acetylene derivatives are dimethyl acetylene dicarboxylate. Because of the presence of 2 electron withdrawing, dimethyl acetylene dicarboxylate can add in a 1,2 addition manner, giving rise to this as 1,2 addition product. Since due to the presence of a 2 bulkier group and it is unstable at under normal reaction condition or temperature, hence it opens up in order to release the strain in the ring system and giving rise to a cyclooctatetraene derivative. So it is, but it's definitely going via, this product is going via 1,2 addition of benzene to acetylene in a 1,2 addition manner. So these are a few examples of addition of 1,2 addition of benzene to alkene, and then in coming lecture we will discuss how benzene reacts with undergo 1,3 addition product as well as 1,4 addition product. Thank you very much.